So, welcome everybody to this online class 3 for multivariable calculus. So, hopefully everyone can see my screen and my audio. If not, then you're in a little trouble. So the first thing to emphasise, as someone's mentioned, is that the first assignment is due next week. The first two questions approximately so the first questions are on curves and surfaces, and the last one is about applications of derivatives, so tangent planes, chain or gradient vector, which I want to touch on today. As someone's already alluded to, is that certainly the tangent plane, gradient rule, chain rule, that sort of stuff, some of that's quite much more like revision than some of the earlier topics, and so perhaps you might be more familiar with that. So what I want to do today is just give some applications for these things, as well as just revising them all. But if you've got any questions, particularly about the earlier topics, which might indeed be more difficult for you, or maybe not, you can fire away if you need to and dedicate that time towards it. So basically, partial differentiation is just how to differentiate when you've got functions of many variables. That's what it boils down to. And you can use it for lots of different things. So the subject looks at a few different applications for that. I just want to go through them. I want to consider where these sort of concepts arise in other sort of areas. That's the basic plan. How are you going? So the first one is I just got some snippets of theory in my notes here, and then some examples for us to work on. So the first application in terms of stuff is a gradient vector, which is pretty much just a vector of partial derivatives. I'll go through an extended example and should have at the end explain so where you might use them into optimization problems. So the directional derivative is the slope in a particular direction. So if you've got a 3D surface, it's just how steep it is in a particular direction. You can work at the directional derivative of any function f in a given direction by just taking a dot product of the gradient vector and that unit vector and that vector. What's really important to stress here, and I want to do it now, is that for it to work properly, this direction must have of length 1. If you don't, that doesn't really make sense. So this direction has to be of length 1. And so sometimes you want to find a slope in another direction which you don't have length 1. So in order to be able to utilize this formula, you need to make it into unit 1 first, so I divide by its length. So what's so useful about this directional derivative is to just slope in any direction. So by a bit of thought, you can work out that this is going to be maximum when the dot product's maximum, which really arises when u here is parallel to the gradient vector. And so one understanding the gradient vector is it's the direction of steepest descent all the time. And you can work out that the maximum value of the slope would be the length of this gradient vector. So the gradient vector is very much plays a key part as about being orthogonal, I guess you want to put it, to level curves or level surfaces, but also direction of steepest descent as well. So important sort of role it takes. And we'll see this idea of the gradient vector and this sort of differential operators. This is a differential operator here, sort of cropping out when we're looking at vector stuff, and we'll see that more again when we return to vector calculus a bit later in the subject. So let's just look at an example. Just copy and paste it. Take a snapshot. Moving across to my other program here. Where'd it go? I sometimes have too many things open, I think I'll find. That's better. You can't see them all, which is probably beneficial for me. Anyway, enough of my rambling. So I want to consider a point on a given surface. Just by way of recognizing it, this here is a quadric surface because all the terms are most squares. Any ideas what type of surface it is? You can guess, it's fine. So just roughly speaking, in order to do it properly, you need to complete the square. But once you complete the square, then you'll have a x squared term and a y squared term the linear terms will disappear using z on this side. So z is equal to sums of, like a sum of squares essentially. Get rid of the signs. And so traces for fixed z's give you ellipses, and traces for fixed x's and y's will give you parabolas. So a parabola is in two different directions. So it'll be a paraboloid, and since it's ellipse in the direction, as someone's correctly said, it's an elliptical paraboloid. So, and because of the negative signs, roughly speaking, it's going to look something like that. That's our really rough shape. We'll get it properly drawn later. But we're going to basically picking some arbitrary point on the surface here and want to know, well, what's the slope? What slope is it? So this is just a simple picture of a hill, for example. So what's the slope at various points? So we're picking a point 3, 1, so x equals 3, y equals 1, and we'll look at some various things. So first of all, let's work out the gradient vector of z. So the gradient vector really is just a vector. The first component is the partial derivative of z with respect to x. The second component is partial derivative of z with respect to y. And we want to work it in general for the moment, and then we'll work it in particular case. So you guys can work it out, I hope. So if you just take the partial derivative of this function z with respect to x, what do you get? You can just type the answer in the chat box, it'd be great. Pardon me. Yep. So minus 2x plus 2 in general, and the partial derivative with respect to y, which would be the y terms. What answer do you get? Yep, minus 8y minus 8. Cheers. And other people can have a go. You can do it on your piece of paper if you want to. Yes, thank you very much, Naomi. And so that's what it is in general. We would like to know what this gradient vector is at our particular point, 3, 1, really. And so that really just means subbing in x equals 3, y equals 1 into this equation. So we're getting minus 2 times 3, minus 6 plus 2 gives you minus 4. And minus 8 times by 1 minus another 8 gives you minus 16. So that's the gradient vector. So and as I said, that's the direction of steepest descent. So if you look at a picture here, that would be much a vector pointing up the slope, so where the steepest direction is. That's what it means visually. And if you did level curves, if I draw level curves for it, it'd be a vector perpendicular to the level curve as well. And I will show that later, actually. So now we know this gradient vector, we can work out the slope in any direction from this point. So we want to work out, we've got this, call it u. So let's find the directional derivative in the direction of u of our function z. And the way to do that is just to take the dot product of our gradient vector with my unit vector. And again, this has to be unit vector for it to work. If you notice, if you take sum of squares, so you do this first term, so 4 on root 17 squared plus 1 on root 17 squared, you end up getting 1. So it actually has length 1. So it actually works. So you don't have to normalize in this case. That's already done. So in this case, it'd be minus 4. Dot product just means multiply by the corresponding terms. So minus 16 times by minus 1 on root 17. So just multiply all matching terms and add them all up. And so if we work out what we get, so we're getting minus 16 plus 16 all on root 17. 17, not 0, equals 0. So that tells you that the slope in this particular direction is 0. What do you reckon that means? So if you had to make a guess, we lost someone unfortunately. So what does that mean to have a slope of 0? Yeah, it's flat. So visually, that means you're running, for a different color here, that means you're running along the edge of the curve. So running along a contour if you've ever done orienteering. So if you're on a hill, instead of running up the hill, you're running sideways so that you're running so you're not going any higher or any lower. So it's called running along the contour. And as a matter of fact, visually, it's sort of in the perpendicular direction to running straight up the hill. So now let's try to work out the slope in some other direction. So I just pick -3, -4, and I've done it. You can specify directions in different ways. So you can specify it as a vector, just specifying all the terms separately. Or sometimes it's useful to write I and J, I just being the unit vector in the direction of along the positive x-axis, and J is the unit vector in the direction of the positive y-axis. And they're synonyms for each other, so whatever you find most convenient, the way to write it down. I like flicking between the two. So most of the time I prefer the vector notation, the standard sort of one, but I do find the other one useful at time to time. So at first glance, you'd think you could do the directional derivative in the same sort of way, and as again you take the dot product of the two, and so you think, oh, it's just going to be the -4 times by -3 plus -16 times by -4, and you get an answer. But that's incorrect. So what's wrong with trying to do it that way? Any ideas? Well, someone's thinking, that's good. So other people can think about it and go, what's... Yeah, so as one person, so a few people have said, you can't do it unless the vector's a normal one first. So you actually have to divide by the length. So first of all, if we call this u, we have to work out the length of u first. So the length of u squared would be the x component squared plus the y component squared, which is 25 using Pythagoras results. And so the length of u would be 5. And so what we really need to do before we do anything else, we need to normalize it. So by putting a hat over the top, essentially, by dividing each component here by 5, which is what someone wrote down in the chat box. So we need to multiply not by -3, but -3 on 5, and -4 over 5 correspondingly. So if you then do the calculations, -4 times -3 gives you 12 over 5. -16 times -4 gives you positive 64. So 78 over 5, or whatever that number equals to. So a bit of, certainly much bigger than 0. So it's getting a bit steeper in that direction. So last two is, what's the direction of steepest descent? I have actually said this already. So how do you work out the direction of steepest descent? Well, the answer is that's just the gradient vector. And so that's going to be -4, -16. That's always the direction. And you can normalize it if you felt like it. It's still same direction though. The slope in that direction ends up being the length of our gradient vector. And so these last two are just sort of standard results. And so that'd be, again, let's square it to make it easier for us all. So it's going to be -4 squared plus -16 squared, which is equal to 16 plus 256. You could do it, but I'm just going to factorize the 16s out. So it's 16 of 1 plus 16. So it's 16 times by 17. So the length of our gradient vector, so slope in the maximum direction, would be the square root of this. Square root of 16 is 4. Square root of 17 is square root of 17. So as a simplified surd at least, the length would be 4 root 17. You can write it on other ways, of course. So I just want to show visually what we've done here. So these are our level curves for this thing. So it's maple, so it doesn't always draw things super accurately unless you ask it. So maple just draws dots to dots. But this is our contour plot, and you can see that there's it's a elliptic paraboloid with a maximum pretty much at x equals 1, y equals -1. So back in the middle there. We've considered the x equals 3, y equals 1. Obviously, you've got some various arrows. So the black arrow here is the gradient vector. And as you might be able to see, basically that is perpendicular to the level curve. And that always happens. That's one of the general results. And it's the direction which is the steepest. So you can see it's actually heading towards the, what do you call it? The center there is not actually the steepest direction. The steepest direction is a little bit different because it's elliptical rather than circular. The blue one was this first case we did, and that was when we got the slope of 0. And you can see a slope of 0 just means you're running along the contour. And the green one was the last one. You can see that happens to be heading towards the center, and it's rather steep slope. Visually in 3D, so this is our elliptic paraboloid on the side. So the peak sort of up the top here somewhere. And you can see that the green arrow is actually pointing towards the peak. That's not my direction we worked at. The black is the steepest direction, so slightly differently, and blue is running along the contour. So I just leave that with the flat one. And 3D is hard to visualize. You can get Maple to produce it, which is where I got it from, and spin it around. But that's sort of visually what we're looking for, to see how they all mix together. So where do you then use this? I mean, yes, you can use slopes. Where else do you use it? So you can use it in optimization problems. So this is an elliptical paraboloid. You can work out what the maximum point is very easily from what we already know. So you just complete the square and you can work it out. But if you had more complicated multivariable functions, the minimum or maximum points often are quite difficult to work out. But sometimes they're really important to do. So an example where I've had to do this sort of stuff is I've got a silhouette, so an image, and I would like to try to fit some data to the image. And at the end of the day, you should work out some fitting function to work out the cost of how good the fit is. And you want to try to make the fit as better as you can, which means minimizing the distance from the image you've got and the model that you're trying to produce it to. So it's a minimizing function based on many variables, as the case may be. And you're trying to get some sort of method to get closer and closer to that optimal value, so the best fit possible. And so there's lots of tricks, but a simple way of doing it is basically, pick an arbitrary point as a starting point. Work out the gradient vector, and the gradient vector tells you the direction of steepest ascent, or if it's minimizing, steepest descent in a similar sort of way. And you just move your example point a little bit in that direction. And since it's going up, since it's climbing, it's going to get closer and closer to our maximum. And you want to move it along a bit, work out the gradient vector a second time, and move in a slightly different direction. So I take my picture here, roughly what's going to happen. So from our starting point, we'd move a bit in this gradient vector, so up to here, for example. Then we work out a new gradient vector, heading in that direction, and always heading in the direction of the gradient vectors. And eventually we'll end up heading towards the true maximum value. That's the basic way of doing it. So that's called the method of steepest ascent, or it's a hill climbing algorithm. And it's a very simple one based on the gradient vector. You can use more sophisticated ones, which basically realize that this sometimes takes a really long time, and there's ways of trying to speed it up. But they all are variations of using the gradient vector and other sort of tools, some sort of compromise between the two, to work out a good way of finding an optimal value. And certainly I've used that for vastly more complicated examples in this paraboloid one here too. And so that gradient vector really is a key underpinning for it all. And working at how it changes like Hessian matrices are important too, which we'll see later on. So trying to impress upon you that we're doing it for more than just being able to do an assignment question. Well, that's all right. Other sorts of things I want to mention is the chain rule. And so the chain rule pretty much in for functions of one variable just tells you how to take a derivative when you've got a function of a function. When you've got functions of multiple variables, it's the same idea. It's just how do you take a derivative when you've got functions of functions. But because you've got multiple variables, it becomes a little more complicated looking. Often you can do these chain rules by just reducing the first function down to just one variable anyhow, and just use your normal rules of calculus and you get the answer. But I just want to show you a situation where it's actually helpful to do it. And again, there's an assignment question if you haven't worked out yet on the same sort of theme as that. So I've got a differential equation here, and in case you're wondering where you normally get these things from, is it ended up being written down as if you do the second derivative of y with respect to t is equal to 4y minus y cubed. So these are the same thing. These are effectively the same differential equations. So the one on the side is the second order one. The one on the right hand side is a first order linear system, and you can go between the other. That's sort of a natural way of doing it. So if you've got a differential equation, you've got one here, the idea is I want to solve it. I would like to know what the sort of solutions I get for y. This here is a nonlinear differential equation, and this one's nonlinear too. And as soon as you get nonlinear, they end up getting a bit harder to work out. Is the long and short of it. And so sometimes you want to do some other sort of tricks to get a qualitative understanding, or perhaps what it is. And so you got to have some other tricks to get ideas of qualified understanding. So what's the dynamical behavior of this differential equation for certain situations? Does it tend to some key points? Does it stay in loops, or what? I mean, there's various options for it. So for this particular one, I've considered a particular function here, which is a function of the variables y and w. And I would like to see how does this function change when I differentiate with respect to time. So I've got my time variable. So to work out the straight derivative of f with respect to time, I really need to use the chain rule. And since I don't really know what the solution is for this whole differential equation, I can't do it explicitly by first solving it all in terms of t and subbing in. I actually have to do it using the chain rule as stated. So the chain rule pretty much says I just got to differentiate my function with respect to my first variable, and then multiply by the partial derivative of that variable with respect to time. It's partial derivative in general because let's get the right variables. Comparison might be helpful. Because y is a function only of t, you can make it a straight derivative as well. Then you do sum, and you do the same for all other variables. So del f del w dot del w del t. That's the basic form of a chain rule. Now it's just a matter of plugging in. So del f del y, you have to work it out. So can someone tell me what the partial derivative of this particular function here is with respect to y? At least put it on your own piece of paper. Scribble it down to make sure you're understanding it all. So del f to y is partial derivative of the first term would be 16y. Partial derivative of the next term would be 4y cubed, and a partial derivative of the next term with respect to y would be nothing. So we multiply that one there by del y dt, or we might just say dy dt. And dy dt, we know from over here, is equal to w. That's sort of our definition of our differential equation. And we do the same thing for the next partial derivative. So partial derivative of f with respect to w. The first two terms have no w, so they don't really change much in the partial derivative. And the last one would be minus 4w. It's our partial derivative. And then we're multiplying that by del w dt, which is just a straight derivative of 4y minus y cubed. What's that equal to? You work it out. Can you simplify the algebra down so you work out what the answer is? Still there, aren't I? Yep. You learn better by doing stuff yourself, which is what I'm trying to force you to do, if you haven't worked that out yet. Everyone's being really quiet. I hope you are doing your own piece of paper. If you are recording, see if you can try to do it yourself. Someone's trying to get in there. Thank you. So I'm lazy, so I would try to I didn't get it right, obviously. Yeah, no, okay, that's fine. So I would just keep the w factorised out the whole thing. Indeed, I'd factorise the 4w. So I've got 4y minus y cubed is the first 4w. The second one has a 4w as well. So minus 4y minus y cubed. So instead of trying to expand everything and simplify, factorise where I can, and those two terms are the same, and you get 0 is the answer. So thank you very much for someone trying, but the answer is 0. So therefore, the derivative of this function with respect to time equals 0. What does that mean? Well, that means that if I then integrated, so if I integrated f with respect to time, then what's the integral of 0 with respect to time? Well, it's just a constant. So that tells you that for my differential equation here, 8y squared minus y to the 4 minus 2w squared is equal to a constant. So this particular curve here, which is not exactly a nice thing to consider, but nevertheless a curve in terms of y's and w's, these curves for different constants would give you different fixed curves that the whole system moves on. So these are fixed curves, and that would tell you that the system has some sort of stable cycles, of funny looking shapes potentially, but there are stable cycles nevertheless. And by drawing some of these, you can work out what some of the things are. So these curves were now producing what's called a phase plot of the differential equation. And you can get so you can have trying to draw them, and what these look like for different constants. They sometimes look like circles, so depending on what the constant is. So two circles, they're not circles, but two closed loops, I should say. And for other constants, you get different sort of shapes happening. So being able to do this is a good way of verifying we've got stable cycles as it happens for this particular differential equation. So that's an example of where the chain rule comes in handy to verify certain things. Again, if you've got any questions, fire away as we go through. I can explain more if you want to. So we can use this idea of the chain rule to find another way of doing implicit differentiation. And that is that essentially by a bit of proof of the chain rule, which is done in the notes if you want to see, you can work out the partial derivative or the derivative of a function can be worked out using just partial derivatives directly rather than having to go through the issue of trying to do implicit differentiation. So let's do an example. So this is a certain function. I like this function. This is what the picture of it is. So I can get my picture. So get a bit of a smaller size, I can deal with it. Okay. So this is the function. It's called a monkey saddle. So why it's a monkey saddle is you can imagine well, maybe you can imagine a monkey. So with its legs on either side. So like a person would have the same sort of thing. So you have two legs, but a monkey, unlike a person, has a tail. So the tail will go up down the bottom, and then the monkey's otherwise at the top. I'm terrible at drawing monkeys, I'm sorry, but we'll have a monkey wave at us. So the key thing about this is it has 1, 2, 3 dips around the side for the monkey to sit on the saddle comfortably. So this is the monkey saddle. And you get all these cool shapes if you want to do it, and it has a pretty simple looking form in the end. And so let's just work out a partial derivative of this particular equation. So let's find the partial derivative of y with respect to x. So essentially this monkey saddle implicitly defines the relationship between y and x. Not explicitly, implicitly. And so we have to use implicit differentiation ideas to try to work out this value. So you can do it directly, and I can do it if you want me to. The method I suspect most people find easier to do is instead using the chain rule effectively. How the result normally works is you dump everything on one side. So let's just, so we've got x cubed minus 3xy squared minus z is equal to 0. So just dumped everything on one side. We'll call what we see on the left-hand side here function g. Let's give it a name. Then the implicit function theorem pretty much states is you take the partial derivative of g with respect to what's on the bottom, so del x, and then on the bottom you do the partial derivative of g with respect to what's on the top. And so far, if you look at this, it's almost treating like the fraction. So if it was all fractions, that would seem to make sense. The one difference that's a bit surprising is you have to put a minus sign somewhere. So I just put it on the top arbitrarily, but it could be on the bottom equally. So that's the implicit function theorem. And really, this is just an application of the chain rule. That's what it really comes from. So in this particular case, we're going to have to work out what the partial derivatives are. So the partial derivative of g with respect to x. So partial derivative of x cubed with respect to x is 3x squared. Partial derivative of this term with respect to x would be minus 3y squared. And the partial derivative of z with respect to x is nothing. So that's the first term. The next partial derivative with respect to y is this one here. And it's what's that equal to? So again, let's hopefully getting you to stop watching and have a go at your own self. Put your own piece of paper. What do you reckon the partial derivative of g, as it define it, with respect to y is equal to? Yep. So yep, minus 6xy sounds pretty good to me. And so our partial derivative of y with respect to x then, which is what I really want to know after all, is going to be the top one, 3x squared minus 3y squared, over the bottom one, with a minus sign somewhere. And so I could just make the minus on the bottom to make it a positive, for example, to make it a bit easier on myself perhaps. And that's sort of the answer. And you can simplify it down if you want to. This common factors are 3, for example. So x squared minus y squared on 2xy, etc. is what you can do. That sort of gives you, and that's the answer. And then if you want to do, you can plug values of x and y in to work at what the this partial corresponds to at various points in time. So lots of different applications. So the last one is the idea of a tangent plane. So you can work out the tangent plane to any sorts of function, and so if you have z is equal to a function of x and y, then this sort of equation is how you work it out. And you can write this very succinctly if you wanted to using the gradient vector. So the idea of using vector notation can greatly simplify much of this work here. And we'll return to that concept very strongly in terms of vector calculus. And I can mention some more here for today. I've got some more in the notes, but to keep it simple, let's go for the more explicit formulas. You can also define a function implicitly. So g is a function of x, y, and z equals 0. And you can also work out the tangent plane in that sort of context too. And the key part is to really know the partial derivatives. The key result is to know the gradient vector effectively at a given point. So I just want to do an example which is not too bad in terms of tangent planes, but just want to suggest where these are actually useful. So this problem arises from working out things in a plane. So how a plane works, a plane needs to know its location and its airspeed and lots of those sort of things to work out, to do autopilots and many other things. So how it works, its position out, is it every so often connects to the GPS satellite and works out its position with a certain degree of accuracy from the GPS satellite. Then it flies along a bit, and before it gets the next little update from the GPS. So in between those two times, it has to estimate its position from knowing other things like how fast it's going, the direction it's pointing in, its internal compass, that sort of stuff. And so at any point in time, it needs to know from its previous information, try to predict, and from other readings it's got, try to make a prediction of where it's going to be next. And some sort of tracking. And then using something like GPS, which is high degree of accuracy, to fix up every so often. So that's the sort of an overall problem a plane has to try to do, and sort of what the navigation systems have to control all of this. So roughly, so let's just focus on one really narrow aspect of that. And so that one particular aspect is we might know already that the speed, the x component speed is, say, 10 meters per second, and the angle it's doing, let's put it in radians, is, say, pi and 6. Then you can work out what the x component speed is after a little bit of time. Pretty much it's the previous speed plus a little bit of acceleration caused by some wind, for example. And it's the component of the wind that's going to be pushing in the right direction. So in the cos theta would be the x direction. And this wind that it gets buffeted about have some random acceleration, and so you can do some fancy stuff by having this random element with sophisticated maths, but let's make it a bit simpler for us for the moment. Let's assume that a is, just say, 0.1, for example, to make it concrete down. So this is our update equation, updating what the new estimate for our velocity is based on our old estimates that we had previously. And a plane would have lots of these updated equations. There are quite a few for all the different variables it needs to know. This particular one here is nonlinear. So v is a nonlinear function of u and theta. If it's all linear, they're a bit easier to handle, and you can do linear algebra techniques to handle that sort of stuff. When it's nonlinear, they get a bit harder, and so as long as you make the updates pretty frequently, then you can do a reasonable approximation of converting these to a linear problem. And that really just boils down to working at the tangent plane. So if you can understand the tangent plane, you've got a good idea of how to update errors, which is what you really know. You want to know how accurate your system is. And also updating your position as well, using this linear equation. So what it really boils down to is knowing this tangent plane is a really good way of updating the system in a straightforward fashion. So the tangent plane in general, so we want to know the tangent plane about a function v in this case. So it's going to be v minus our point in question. Let's call it v naught. And it's going to be equal to our partial derivative of v with respect to u at our point in question. So u naught theta naught times by u minus u naught plus the partial derivative of our value v with respect to the next variable theta at our point in question, and then our theta minus theta naught. So we've got to work out a few things here. So we've got u naught is 10, theta naught is pi on 6. So that's our estimates for what it really is. They might not be the real values. It could be a little bit more or a little bit less. So there's some degree of error. And so u and v here are the real values, u naught and v theta. So u and theta is the real values. U naught and theta naught are our hopefully good approximations is the idea. So these are good approximations. And if you plug these numbers in, you can work out what v naught is. Internet's okay. Can you guys still hear me? I just have this feeling my internet's dropped out temporarily. That doesn't sound good. Anyone? Okay, good. Thank you. Get worried for a sec there. So plugging in the values, we can see that v naught is our estimate is going to be 10 plus 0.1 times by cos pi on 6, which is a half, which gives you 10.05. So our tangent vector, so we're not going to have v naught, so we got our reference frame, and then we work out some partial derivative. So vu is just another way of saying the partial derivative of v with respect to u, and that's just going to be equal to, in this case, just 1. The partial derivative of v with respect to theta, which is written as v del theta, you can work out similarly. It's going to be 0.1. Derivative of theta is minus sine. And so at our reference point, so vu at u naught, theta naught, well, it's 1 all the time, so it doesn't really matter what point we're subbing into. It doesn't change anything. When we sub in our reference point into theta naught, we're getting minus 1 times sine pi on 6, and that's where I realised I made a mistake. Sine of pi on 6 is a half, so that's minus 0.05. And I realised that that's not 10.05, that's something bigger. That's 0.8, isn't it? So 10.08 approximately. So it should be root 3 on 2 instead. So cos upon 6 should be root 3 on 2. It's the bigger number. So I got it slightly out. So sorry about that. You can write it better than me. Put a few dots there. And so now we've put all the tangent plane together. So we've got v minus v naught, which is 10.08 approximately, is equal to this partial derivative of 1 times by u minus u naught plus now next partial derivative theta minus theta naught. And that gives you our version of our tangent plane. And so V is, so where we can use this tangent plane is, now if we have some idea not what U is, it's 10, but also if we know that U is, if we know what the amount of error we have for U and the amount of error we have for theta, we can then start estimating errors for V, etc. as well. And that sort of tricks that you can apply. So this whole idea of what this is alluding to is this tangent plane idea effectively makes nonlinear equations into linear ones. That's effectively what it does. And so this whole big process I'm talking about is called an extended Kalman filter. It's a fancy name for it. So a Kalman filter is when you've got a completely linear situation where you've got, some measurements with some degree of error, and you've got some updated equation, and then you've got some external reference point to verify if it's right or not, and you have some sort of weighted average between your external measurements and what you're already going for. And this idea is used in Hawkeye and cricket, for example. So when the ball's travelling through space, there's 6 cameras in cricket, and they take a picture of the ball. Not all the time, but 50 times a second or something to that effect. So every 50 times a second, the cameras give an idea of where the ball is. The cameras aren't accurate either, although they're calibrated. They have some inaccuracies. And so Hawkeye, every 50th of a second, will make a prediction based on what its previous ideas of where the ball's going in terms of spin as well, and then combines it with the image it's got and takes a weighted average between the two. That's a linear problem. But when you're getting some nonlinearities cropping up, then you have to do some fancy stuff. And one way of trying to make it doable is to basically linearize each step, essentially by putting in tangent planes or equivalent to that, which is what this one's trying to do. So again, just trying to press upon you that tangent planes aren't some silly thing, but a really helpful technique sometimes to try to handle nonlinear problems. Okay, so that's sort of the main things I wanted to cover today, but I'm happy to answer your questions. So as I said before, make sure you complete the assignment. I've got the wrong date here. So it's the next week, so 22nd of March 2017 is when your due date is. So I haven't quite updated that. The marking criteria do try to spell out how to do various things. And so I guess the last thing I want to talk about is there's lots of graphs in there. And so for the graphs, you are encouraged, I would say, to use Maple. I think that, or a program like that. You don't have to use Maple, but some sort of program to help you draw the pictures that will make them a bit easier for you. The problem with the computer is they don't put any labels down, and I want you, once you've got stuff from the computer program, to try to understand what it's trying to say. You've got some 3D figure, which way is it really pointing? I want you to have understanding what the computer is giving to you. And so that's why I want you to try to label it. And so for a 2D graph, that's not too bad. So if you just look at my pictures here, which I haven't labeled at all. So for a 2D graph, it's not too bad. You can put an XY axis in quite easily and you can see it and see exactly where it is. And labeling key points like a vertex here, you can sort of do. You do have to vary the contour plots like this one here is here. If I chose a contour to be exactly where the maximum point is, it'd come at just as a dot. And unfortunately, a Maple would just draw the dot as being nothing there at all. And so you have to be aware that sometimes a contour plot may not crop up properly in Maple's pictures, and be wary of that. You might have to fix that for your assignment, by the way. For 3D graphs like this one here, you can see that without the axes being put on, it's a bit hard to work out exactly what it is. You can tell it's, you might be able to tell it's an elliptical paraboloid. The fact it looks, you can't tell it's curving around the other side because of the choice of axes I've got. But so for those sort of shapes, it's important to label key points. So if you can say there's a maximum vertex at the top here, that would make it a really solidify. Go, oh, okay, I can see there's a maximum point. Must be some sort of paraboloid. You've got a better sense for it then. But also you need to give some sort of orientation, I think is useful. You can do it lots of different ways. So in this situation here, if I follow the mouse again. So if I was trying to do label this sort of picture for an assignment question, I would be keen to label the vertex at the top, which is from memory. Look at the picture. X equals 1, y equals -1. If you plug that in, I think you get 5. So that's a vertex at the top. And then label axes to give it orientation. And a simple way of doing that, I think, is to just put the axes through the center here, so that they would be the key axes here. This one happens to be, well, parallel to the z-axis, but I've picked it so that it passes exactly through the center. So this one here really is x equals 1, y equals -1. So this is a straight line here, and it's not the z-axis, but it's parallel to it. And that makes it much clearer to me what the orientation of it all is. And you can do similarly label these bottom ones here. So this would be x equals 1, z equals 0, and this one is y equals -1, z equals 0. Or maybe the other way around. So I've done it too quickly. So that's one way of labeling them. So you get a sense of both what the shape is. You can see that roughly from a rough sketch, or the maple, etc. Labeling a key point just to fix it in space, and some sort of labeling to give you orientation. What I've done there is not the only way of doing it, and so you can get the computer to help you put some axes on. So Maple, just right click and say axes, and it can help you out. But labeling key points you probably have to do after the fact regardless. So just giving you some ideas what to do there. So make sure when you're doing your questions, don't just read the question, but also look at the marking criteria. Sometimes they give you big helps for some traps that you might have otherwise encountered. And just give you, make sure I don't forget that. So that's what I may want to cover today. So please have a go at the assignment. Any questions that people have? So anything that's jumping at you going, oh, don't really get that. Yeah, just a general question is fine. Just waiting for you to type in, as everyone knows that I'm. So should we be working through all problems, Stuart? So is your question. The goal that I give to students is that you should work through all the tutorial problems, which is a smaller set. So there's tutorials, say 10 tutorials at the back of the study guide, and so that's what I encourage you to work through. If you can handle those questions, so if you get through all those going, I know what I'm doing, that's probably enough for the subject. Sometimes you get through and you go, you have to keep flicking back to the answers. So sometimes people go through them, speaking generically here. If you draw these questions and go, I got them stuck, you flick back to the answers, which are given there in the study guide, and you go, I get it now, and you'll maybe just get help bits and pieces. And if you've got through that tutorial questions and you're going, look, I've got the answers because I've had to look at the solutions a lot, but I don't still feel confident with it. And in that case, that's when I would flick over to do some more questions from Stuart. And confidence really depends upon you. You might need many more questions there, confidence, or get things worked up. Now you guys know how well you learn, so I don't think you need to be aiming to do that. But some of you might need more practice than others to get on top of it. So that's my basic answer for it. Any other questions people have got? Well, thanks for your time. I won't leave just yet, but I will stop the recording. So thanks everyone for your time. And so if you do have questions as you're going through the assignment, so this weekend, etc., fire away, and I can discuss a few more things at the start of next week's lesson if you need to as well, or in between. I'm happy to answer questions before that time if you need it. But anyway, thank you very much for coming.